So now we're going to move on to the empirical rule. The empirical rule applies when your data is bell-shaped, which we call normal. Remember we talked about normal distribution a few other times? If it's bell-shaped, and what it says, there's a lot of symbols this penny time. A lot of symbols on that picture on your notes there. So notice in the middle here, see this one shows up better. No, it doesn't. I have to go hunting for my black. I found my black pen. Look at that. There's a mu in the middle. What's mu?
Population mean?
Population mean. If your data is bell-shaped, that's a very steep bell, but if it's bell-shaped, the population mean is what you would expect to be right in the middle. That's why the mu is in the middle. You expect more people to have that number than anything else. And then these little sigmas down here represent what?
Population.
Population standard deviation. This bell-shaped curve, by the way, I get a little sloppy. These little edges here get closer and closer and closer to the x-axis without ever touching. I get a little sloppy in how I draw it. If you look at it on your paper on page 29 there, it looks like they're touching. The problem is they're so close you can't really tell the difference. But technically they just get really close and hang on to that. They never touch, but they're so close they might as well eventually. It's so tiny. It'd be like if I asked you to paint underneath there. At some point you wouldn't need any more paint because it's so skinny that you can't fit your paintbrush in there, right? And then so these little sigmas here, in a way they should actually have like little plus signs in them because we're going to add sigma to get to the next one and we're going to add sigma to get to the next one and keep counting by standard deviations. So we're saying start in the middle with your mean, add the standard deviation, add the standard deviation, add the standard deviation. And if I'm going to the left, guess what I'm doing?
Subtracting.
Subtracting the standard deviation away from the mean. I'm going to add and subtract there. And before I talk about the rule, I'm actually going to label this to match the example underneath. It'll make way more sense. Let me put it here. So I'm going to draw that same picture. You can just label it right underneath it if you want. Look at the example there about the heights of women. It says that women heights have a bell-shaped curve with a mean of 161 centimeters and a standard deviation of 7. So what am I going to do with the 161?
In the middle?
Put it in the middle. 161 goes right in the middle. And then I have to mark my scale. If you're drawing them by hand, I have this one drawn for you. If you're drawing them by hand, see where it's like curving down and then curving up, right about here, like where it stops going down and starts flattening out? That's usually 1 standard deviation away. Roughly like this, evenly spaced. I'm going to add and subtract the 7 now. 7? Yes. So the next number over here would be 168. If I add 7 again, 175, and I add 7 again, 182. We all right where those numbers are coming from? Adding the standard deviation. And then if I go this way, I'm going to subtract the standard deviation. So 161 minus 7 is 154. And if I subtract 7 again, let me squeeze this in here a little bit better. 140? I'm subtracting in my head. Tell me if I'm wrong. Okay, I got my subtraction down for the day? We're good. Okay, so this number line describes women's heights. We would expect most women to be around 161 centimeters. Some people are taller, some people are shorter. Hardly anyone's taller than this. Some people are. It's a little skinny little sliver over here. And hardly anyone. Most people are closer to the middle. And then you can go further and further out. So this represents our bell-shaped curve. Now let's talk about this empirical rule up above. It says about 68% of the data are within 1 standard deviation of the mean. Within 1 standard deviation of the mean. What does that mean to us?
154 to 167.
Ah, 154 to
168.
to 168 he means. So let's point at it. So these people are 1 standard deviation below the mean. These people here. These people are 1 standard deviation above the mean. Just from here to here. Oops, right there on the line. And everybody in between there, if I kind of like connected this again, everybody in there is no more than 1 standard deviation away from the mean. No more than 7 away from the middle. See how I got that?
Because it's 7 and 7.
Because I added 7 and I subtract, that's why I counted by 7. This person is exactly 1 standard deviation higher than the mean. This person is exactly 1 standard deviation lower than the mean. So all these people are 1 or less standard deviations away from the mean. If we drew lines going straight up from here and shaded this in. Now your picture's probably better than mine because I freehanded this one. It should be that about 68% of this data, of this picture, is shaded. 68% is around 2/3, roughly. 2/3 of it is shaded in now. Do we agree with that? Mm-hmm. Your picture's probably better than mine. So we're saying that around 2/3, 68% of people are all going to be within those height ranges. More than half of us, for sure. So the rule is 68% are within 1 standard deviation. 95% are within 2 standard deviations. So if we start in the middle here at the mean, 2 standard deviations takes us out to here, 2 steps above, all the way out to here. Or 2 steps below takes me to here. And so imagine if I shaded everybody in between there. I'm going to make it polka dotted. Otherwise it's going to be too messy. This should now visually be 95% of it is shaded. And it should look like 95, like what, 5% left? Hardly any left. So 95% are between these two heights. And then finally, the third one is 99.7 are within 3 standard deviations, which is hard for me to say apparently. 3 standard deviations. If your picture looks like mine, there's hardly anything left after you go between here and here, right? If we, I guess I could do all over here. Giant stripes here. The blue stripes go all the way from here to here. That's not everybody. Not all women are between 140 and 182 centimeters tall. What percent are not in there?
Says
I'm hearing 0.3%?
yeah.
0.3? Where are we getting 0.3?
It's what's left from 99.7.
Yeah, you think 100% is all women. If you subtract 99.7%, you're left with 0.3%. These little, what we call tails, there's like a little tiny sliver over here and a little tiny sliver over here that you can barely see. In there is 0.3%. A few women, just a few. It's like 3 out of every 1,000 women. 3 out of every 1,000 women are either that tall or that short. So that's the empirical rule. Some people call it the 68, 95, 99.7 rule. Because it's always those numbers. 68% are here, 95, 99.7. Okay with the rule, what it tells us? Now we should be able to quickly answer questions A and B there then. Question C might be tricky.
Yeah, that's
What percent of women are between 147 and 175? I heard some people over here say 95%.
yeah, that's right.
And she's agreeing with them. Where'd we get that? I didn't do any work.
Because it's 2 values, 2 standard deviations from the mean.
147 to 175. Remember, this is mu right here in the middle. So she says that's 2 standard deviations below. That's 2 standard deviations above. So all those people are within 2 standard deviations. They're not more than 2 standard deviations away. And that's what the rule tells us. That's 95% are within 2 standard deviations. Okay with that one? There's no work to do besides recognizing it was 2 steps away. Alex, are you good?
Yeah, I'm good.
Okay. You get this look on your face like, what is she talking about?
Processing.
It's all right. Processing is good. I just want to make sure you don't have questions. Okay, how about B? 99.7% of women are between what two heights?
140 and 182.
140, she says, and 182. Where'd she get those?
They're 3 standard.
She knows where she got them. Somebody else help her out. How'd she get that?
That's 3 standard deviations.
Thank you. That's 3 standard deviations away. 1, 2, this is 3 standard deviations away, and 1, 2, this is 3 standard deviations away, and that's the 99.7 part of the rule. That's not too bad. Question C is kind of tricky though.
I got it.
You got it already?
Yeah.
Nice. Let's do question C. What percent are between 154 and 182? I'm going to erase all of my shading here, which is messy. You have the answer already? Let's write it down and we'll check to see if you're right. Go ahead, tell me the answer.
83.85.
He thinks it's 83.85%. I have no idea how he got it, so I'm going to put a question mark. We're going to check that in a minute. I don't know the answer either. We'll figure it out. We'll figure it out together. If he did get it, he's just showing off. Somebody has to. Good for you. I'm just erasing all my shading here so we can talk about this one. If you need to redraw the picture, you can do that too. Okay, so between which two numbers?
154 and 182.
154 and 182. So from here all the way out to here. There's lots of different ways to get here. I think there's already think he's got it figured out. I'll be right.
That was it.
Yes.
Okay, so, which,
Go ahead, tell me what you're thinking.
Okay.
We're just thinking out loud right now.
so I took the, like, half of 68% because it started 154, and so since it's like okay, I don't know if it's.
No, I totally know what she's trying to say.
So it's like 34% is, it's just that sliver, and then if you start in the middle again, and then go all the way to 182, it's 99.7, and then if you divide that by 2.
Okay, hold that second part. Everyone okay with the pictures right here?
Uh-huh.
She's telling me that's half of 168. Excuse me, half of 68%, not 168. Half of 68%. What does she mean by that? Why? She's right. Is that what you did too?
Yeah.
Why is that green shaded area half of 68? Yeah.
Because it's half of that first deviation.
Right, because this is 1 standard deviation away. 1 standard deviation goes both directions though. If I could have done this whole thing from that blue line to this line, in here, everything in here is 68%. We agree with that? From here to here is 68? We agree have exactly half of it? You see that?
Yeah.
So this little green piece here is 34%. Now, the next thing that she wants is we need to add to it, I'm going to keep it green here, everything out to that 182 over there. So we've already done the diagonal green. Do we agree that the entire green section is what we're asking for? From 154 to 182? Yeah, I got lots of nods here. The green section is what we want. We've already figured out this green part. I'm going to put a little solid line here. The left-hand green part we found. And so then, look at this piece. This piece right here. It's half of something else. How many standard deviations from the middle am I? 3.
So 99.7.
99.7, but it's half of it. So this piece over here, how do I find half of something? Divide by 2. What do we get?
49.85.
49.85. So the left-hand green side is 34. The right-hand green side is 49.85. I want all of that green area. So what do? Add them up. 34 plus 49.85. What do you know? 83.85. Nice job. It's not a question mark anymore. Sounds like a puzzle. Let's break it up wherever you need to. That was a little bit harder. Remember, you always have the 68, 95, 99.7, and you just figure out, do I have the whole thing, do I have half of it? And usually if you take the left hand and the right hand side separately, it's a little bit easier. That's why we broke it up that way. That won't kill us. Questions? We were feeling good to the last one. The last one's a little weird. Okay, we're going to do some more with the same picture, actually, on page 30. Starting section 3.3. It's actually using this same picture. So you might want to, somewhere on the top of page 30, is recreate this same drawing with the same numbers on the bottom, because my example here is still mentioning everything that we just talked about there. The heights of women. So somewhere in there, see if you can recreate that drawing. Roughly a normal curve, 161 in the middle, standard deviation of 7. So we're going to put the same numbers here. It just helps to have it on this next page too. Bless you. I'll talk about the formulas there in a second, at the top of the page. But the example, notice, talks about the same women, the heights and all that. That's why I'm drawing the same picture now. That makes the formulas and everything else make sense. So there's 2 formulas there. I'm going to write them down here so we can talk about them. X minus x bar over s. X minus mu. Oops, there's no x bar in this one. So I have the 2 formulas that are given to us, and I just recreated that same drawing to go with the example here. We're talking about women's heights again. Let's talk about these 2 formulas. What is similar about them? They're both z equals. What else is similar? What am I doing on the top here in words?
Subtracting x from something.
Subtracting x from something. X bar, what's x bar? Mean. So I have x minus the mean. Over here I have x minus, the mean. What's the difference? Sample versus population. So the formula is the same, it just depends on if you're working with a sample or working with a population. I'm taking x subtracting the mean, or I'm taking x and subtracting the mean. This is a sample mean, this is a population mean. Over here I'm then going to divide by
Sample deviation.
standard deviation, if I can speak. This one's for the sample, and this one is for the population. So both of these formulas are x minus the mean, and then divide that by the standard deviation. Maybe you're working with a sample, maybe you're working with a population, but the formula is the same. So let's talk about what the heck those formulas are. They're called z-scores. By the way, I always cross my z's like this when I write them, because otherwise I think they're 2's. And I got in big trouble in calculus one day for getting all my 2's changed, or z's changed into 2's, and so now I always write them this way. You write z's however you can. I can't read my own writing. I can read it now. I did this for years. Okay. So before I find the z-score, I want to answer question B. Question B, page 30 at the top. How many standard deviations away from the mean is a woman who's 170 centimeters tall?
Almost 2.
Almost 2, she says. I'll kind of visually look at question B here. 170 is roughly right in here.
Maybe 2, right?
Everyone okay? I found 170 on my number line. So from here to 168 is 1 standard deviation. And if I go all the way to 175, that's 2 standard deviations. So how many is it?
2.
1 point.
1 point something. We agree with that? Somewhere between 1 and 2 standard deviations away. Think it's closer to 1 or closer to 2?
One.
Yeah, looks like it, because 170 is closer to 168. So is it more or less than 1.5? Maybe less, like maybe 1.2 or 3. I can't tell for sure by looking, especially if you draw like I do. So maybe 1.2-ish. All we can do is visually kind of estimate if we have the picture. We're okay with where that 1.2 is coming from? That's our answer for a guess. We're going to get the actual answer here in a second. I like to talk about it first so that you understand what the z-score formula does. Are we all right with where I got 1.2, what it represents? Okay, what I want to do now is find the z-score up in part A, and then we're going to talk about part B again. It says find the z-score, which means plug stuff into our formula. So we want to find z for 170. So they're telling me that x is 170. That's the specific value they're talking about. We want to turn that into a z-score using our beautiful formula. So z equals, I take my x and I subtract.
By the sample mean.
By the mean, which in this case was 161. We agree with that? Whether it's a sample or a population, I'm subtracting the mean. By the way, which one do I have here? Am I working with the population or am I working with a sample? Sample? How do we know that?
There's a sample of all women.
Oh, all women. Uh-oh. All women. If we're talking about all women,
That's a
that's a population. So the statement that says heights of women have this bell-shaped distribution, it doesn't say some women, it says women. So they're actually talking about the population. The mean here is the population mean, and the standard deviation is the population standard deviation. If it had come from a sample, it would have said something like a group of women had this mean and this standard deviation. But when it just says women, that means they're talking about all women. It doesn't really affect our calculation. I just like to point out that sometimes we have all, sometimes we have some. So I'm technically using that formula. And then what am I going to do? Divide by 7. I'm just plugging in my x, my mu, and my sigma into that formula. This turns out to be 9 over 7. Someone divide that for me and round it to 2 decimal places, please.
It's 1.2.
1.28?
1.29.
If we round, is it 1.29?
Yeah, 1.29.
So z equals 1.29. That is the z-score for 170. That was what question A asked for. Question B was, remember we talked about it already, we said we think it's 1.2. Question B is, how many standard deviations away from the mean is that? Guess what the actual answer for B is?
1.29.
1.29. I cannot tell you enough that a z-score is a number that tells you how many standard deviations away from the mean are you. I mean, that's what a z-score tells you. So there's a weird formula. So looking at this here, say the 182, what should I get if I calculate a z-score for 182? No work involved. Well, how many standard deviations from the mean is 182?
3.
1, 2, 3 steps away? So guess what the z-score is?
39.
3. 3 steps away from the mean? Standard deviations? The z-score is 3.
So that's only if it lands on one of the 182, 175, 168.
Right, well,
So
it's true for any of them. So even this one, the z-score is also the answer to how many steps away from the mean are you.
right, but it requires more calculation.
Yes, it requires more work if it doesn't land on it. You're right, sorry, if I get where you're going. If it lands on there, you can see the z-score. But if you can't tell if it's in between, you have to do the calculation. Okay with that? How about 140? Question says, how many standard deviations from the mean is a woman who is 140 centimeters tall? I'm hearing some people over here say 3. You guys are close.
Is it
Negative
-3?
It's actually -3. So we actually have positives and negatives to tell us if it's above the mean or below the mean. Let's do the calculation to show you why. The z for that one would be 140 minus the 161 divided by, what's the standard deviation? 7. So this is the x they asked about. Put it into the formula.
No, because it's gonna be a negative.
Negative 21 over 7, negative 3. So you're right, it is 3 standard deviations away, but it's important to say that it's 3 standard deviations below the mean.
Because it's moving to the left.
Because it's to
not
the left. So a negative 3z right here tells you it's below the mean, and a positive would be above the mean, yes.
And they're always going to tell us our standard deviation, right?
Yes, if they don't give you the standard deviation, we can't say how many of that away it is, right? If they just said the mean is 161, and how far away is this? Well, I don't know how am I moving by counting by 7s, am I counting by 50s? You have to know the standard deviation. There will be times when we have to calculate it first, but you will have it. So we could have just looked at it and seen the negative 3, because it's 1, 2, 3 steps below. Above is positive, below is negative. All right. Right in the middle of page 30 is one of the typos that we need to fix. See where it says unusual values? Here it says unusual. I want you to cross that off right above it and write significantly high / low. Right in the middle where it says unusual values. Cross off the unusual, replace it with significantly high low. It's a little bit more clear what we're talking about. Right in the middle of the page. Significantly is hard to spell. Did I have it wrong? Significant, I think it's right. So it says here that values that are more than 2 standard deviations from the mean. Unusual ones are less than -2, higher have +2. Let's talk about what that means here. 175 is 2 steps above the mean. Any height larger than that is a significantly high height for a woman. It's higher than what you would expect. Our old book used to call it unusual, which is why you're going to see unusual crossed off throughout the notes. But this is, anything above that is significantly high, and anything below 147 would be significantly low. Everyone okay with that? Think of it as extreme value. What's an extreme height? Significantly high, significantly low. So are either of these heights that we talked about here, the 170 or the 140, are either of those significantly high or significantly low?
140 is significantly low.
We agree with her? 140 is significantly low because
It's more than 2.
it's more than 2 standard deviations below the mean. Because it is more than 2 standard deviations below the mean. What's a shorter way to say that? In terms of z-scores. What's the z-score?
Maybe you just put z equals -3.
Z equals -3, and what's the cutoff z that tells me something significantly low? 2, close, we're talking about low. On the low end, it would be -2. Anything below -2 would be significantly low. So you could say -3 is below -2. I mean, that's really what we were doing. Remember, how many standard deviations away is the same as what's your z-score? So that's what that's saying there. Higher than +2 or lower than -2, more than 2 steps away is significantly low. Let me get a visual going here. On my number line, anything past here this way is significantly low, and 2 steps this way, anything above there is significantly high. So what about the 170? Was it significantly high or significantly low? Neither. Right, because it's not even 2 steps away yet, so it's not more than 2 standard deviations away. So it keeps swinging it off. Questions on that? Okay. So let's look at the next question. More with standard deviations here. Which is a better score? So you have 2 different classes. In one class, you've got a 76 on a quiz, where the mean score was 64. Let's stop right there. If the mean was 64, what's that mean?
You got it really high.
It's like the average, right? And then your 76 is above average.
Yeah.
Right? So you got above average, 76, where the mean was 64 and the standard deviation was 6.7. You got an above average grade. Or there's another place where you got a score of 12 on a quiz with a mean of 10. Again, you're above average. But it has a different standard deviation. Standard deviation is 1.1. So the question is, which one is better? They're both above average. She thinks it's the first one. You do too? Everyone agrees it's kind of hard to tell which one's better? Because the numbers here are different. If you were to put the mean and standard deviations, you'd have 2 different pictures. They're both above average, but which one's more above average? You can't just say the top one's more because the standard deviation is more. The numbers are spread out more. I'm going to draw a picture to go with both of these. One picture for each. I'll probably draw this picture another 200 times or so this semester. That's an estimate. So let's draw a picture for each scenario, so we visually know what the heck we're being asked. So what was the mean on the first quiz? 74? Oh, 64. 64, this is the quiz one. The mean was 64, and what am I going to do? Count by the standard deviation, which was 6.7. So I'm going to need my calculator for this. So I'm just marking, by the way, the standard deviations keep going forever. I just marked the first 3. So when I add 6.7, I get 70.7. What's that going to be? 77.4?
Yeah.
Is that right?
Mm-hmm.
Trusting you in my head. What's the next one?
84.1.
84.1? I could keep filling these in over here, but what number am I interested in?
76.
I want to know where 76 is. Right, because 76 is the one that we're asked about. So 76 appears to be roughly right here. There's where that 76 is. Not quite 2 standard deviations above the mean. That's one of the questions they're asking about. And let's draw another picture for quiz 2. Quiz 2, same picture. The mean was 10. And the standard deviation was 1.1. So I'm going to add 1.1 and add 1.1. Is that right? 12.2?
Yeah.
And 13.3. Again, I could add the other way, but I'm only interested in what number? 12, right? And 12 looks to be about right there. There's the 12. So based on my beautiful pictures, which one looks like it's higher?
The second one.
The second one?
They look the same.
Well, they look the same to me too, especially with my fabulous art skills.
One's only 0.2 away from being 2 standard deviation, and one's further away.
Okay, so some of you are saying this is only 0.2, but this is 1.4, but be careful because this is a bigger space, right? This represents 6.7. It's like, how much is that space? They look identical.
So do we make it like a proportion?
It's kind of, she said, do we use a proportion? Actually, what we're going to use is a z-score. We're going to find the z-score for 76, and we're going to find the z-score for 12, and be able to tell which one is actually higher by comparing z-scores. So how do I find the z-score for 76? use the formula for the Z formula. So I start with the 76 minus the mean divided by the standard deviation. This is the information from the first quiz, right? We were given mu equals 64, sigma equals 6.7. We were given for the first one. So I plug that in there. Subtract first, then divide. Tell me what you get.
0.179.
Try again. It's got to be 1 point something.
1.79.
1.79. How'd you get a 0? Double check that for me. Because we can see from the picture that it's 1 and some more. Was that you, Hannah? Yeah, subtract that again, see what happens. I don't know what you did. Just double checking her work. Anybody else have a question on where that came from? Did we round this correctly?
Yeah.
Yeah? Okay. You got it? Yeah?
Yeah, I missed my decimal.
Yes, that'll happen. So over here, we were given that the mean was 10 and the standard deviation was 1.1. So I'm going to do the same thing over here. 12 minus 10 over 1.1.
1.82.
1.82.
So the second one. So that is 10.
Everyone agree with that? What does that mean? Which score was better?
The second one.
The second one was better because it had a higher z-score. Higher z-score. This was the better overall score. Now, mind you, they were darn close. This one was 1.79 standard deviations above the mean. This one was 1.82 standard deviations above the mean. It's slightly better, but not much better.